Hi, a very good day to Dr. Johanna. So we are from Group 4 are going to present Experiment 3 Major Losses in Pipe. Our group consists of me, Majeswaran, Lim Enki, Lee Wei An, and Manikandan. Today, our presentation consists of summary, objective, apparatus, theory, methodology, result and discussion, conclusion, and reference. Hi, so let's have a brief look on the report summary. So we have to understand that when a fluid flowing through a pipe, it's experiencing some resistance due to which some of the energy of fluid is lost. So energy lost through friction in the length of pipeline is commonly termed as major loss, which is loss of head due to pipe friction and to viscous dissipation of flowing water. So the resistance to flow in a pipe is a function of the pipeline, pipe diameter, mean velocity, properties of the fluid, and roughness of the pipe if the flow is turbulent. But it is independent of pressure under which the water flow. So this experiment was carried out to determine the major losses in pipe, and the pipes that are involved are galvanized steel pipe, copper pipe, and three variation of PVC pipe different in diameter. So there are a few methods involved to determine the friction coefficient of the pipe, which includes by using Moody formula, Colebrook formula, Blasius formula, or alternatively, it is obtained directly from Moody chart. So for methods involving the formulas, the friction coefficient is obtained by inserting the data that that require data from the result table. While for Moody chart, it requires some interpolation method to determine the Reynolds number and then refer back to Moody chart to obtain the friction coefficient value. Thank you.
Objective of this experiment 3 is to determine the pipe friction factors divided by resistance coefficient, and the apparatus used for this experiment are retrometer, 2-tube manometer, 6-tube manometer, differential pressure sensor, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, interchangeable measuring objects, water tank, drain valve, pump, various measuring section, feeding hose, gate valve, and thermometer. Thank you.
All right. So for the theoretical part for this experiment, generally, interbillion pipe flow between 2 points of the horizontal pipe, which has constant internal diameter. The total head loss can be determined by using the Bernoulli equation as stated in equation 1 and equation 2. So for turbulent pipe flow, the pipe friction coefficient depends on equivalent pipe roughness, which can refer to table 1, can be referred to table 1, equivalent roughness for the pipe, which is different for each type of pipe. And then the Reynolds number can be calculated by using the data of internal diameter, velocity, and kinematic viscosity of flowing medium. Right, so for kinematic viscosity, we can refer to table 2, the kinematic viscosity of water as a function temperature. And then for the speed of flowing medium, we can calculate by using the data of internal pipe cross-sectional area and flow rate, as we can see in the formula. And for coefficient friction, there are three types of formula involved, which is the Blasius formula, Colebrook formula, and the Moody formula, which all has been attached in the slide, as we can see. Or alternatively, we can directly obtain the value by using a Moody chart, which has been attached in the previous slide. Thank you. All right, let's have a look on the methodology of for this experiment. So it involves 9 steps. Number 1, we have to connect both feeding and a return hose to the tested pipe section. Number 2, we have to connect the manometer to the inlet and outlet of the tested pipe section. Number 3, we have to turn on the main switch and pump, slowly open the gate valve, and wait until the reading of the rotatometer reach 2 meter cube per hour. And number 4, we have to open the ventilation valve on top of 2-tube manometer by turning it anti-clockwise if there are any bubbles present. If there are no bubbles present, we have to turn it to clockwise direction. And number 5, we have to close the gate valve and turn off the pump. Slowly open the ventilation valve on top of 2-tube manometer until the preset minimum reading reach 25 mm for galvanized steel pipe and PVC pipes, while 1 mm for copper pipe. And number 6, we have to slowly open the gate valve until the level of 2-tube manometer of H1 reach maximum while H2 reach the minimum point. And we have to record the value for 2-tube manometer, temperature, and the actual flow rate. Then we have to reduce the actual flow rate to 5 different values by adjusting the opening of the gate valve. And we have to record all the readings. And step number 7, we have to transfer the manometer tubes at the 2-tube manometer to the differential pressure sensor, and we have to record the differential pressure sensor for 5 different values of actual flow rate in step as stated in step 6. And then if there are no bubbles present, we have to close the ventilation valve and record the actual flow rate and the differential pressure reading, because we have to make sure there are no bubbles present in the system. And step number 8, remove all the manometer from the system, close gate valve and turn off the pump before changing the feeding and return hose to another pipe section. And we repeat step 2 to step 8. And then after finish, we have to remove all the manometer tubes from this system, close the gate valve, and turn off the pump and the main switch. Thank you.
In experiment 3, several repeated experiments are carried out and the data are recorded in the tables for each material of pipe. There are 5 tester pipes in this experiment, which are galvanized steel pipe, copper pipe, and 3 PVC pipes with different dimensions. So first, the length, diameter, and the thickness of each pipe tested are measured and recorded. Next, the value of the rotameter, which also known as actual flow rate, and the temperature of the water are recorded in a table. Besides, in this table, the water level at 2 manometer also be recorded as H1 and H2, and the difference between both water levels are calculated and recorded as well. Lastly, the reading of the differential pressure also be recorded by using the differential pressure sensor. Experiment 3, we have 3 discussions. First and foremost, I'm going to discuss about the comparison of the coefficient of friction, which is known as F, for each tester pipe that obtained from the Moody chart and calculation using Blasius, Colebrook, and Moody formulas, as well as discuss the possible reasons for the difference in the values. The coefficient of friction, or sometimes we call it friction factor, is a dimensionless factor that depends on various parameters. So, before we determine the values of the coefficient of friction, we first determine the parameters such as internal diameter of the pipe, average flow rate, velocity of the flow, temperature of the water, kinematic viscosity, Reynolds number, equivalent roughness of the pipe, and lastly, the relative roughness. First, among the 5 tested pipe, only the galvanized steel pipe is provided internal diameter. So for the rest, we use the formula which is outer diameter minus double thickness of the pipe to find the internal diameter. Next, the average water flow rate for each tested pipe is determined using equation summation of the water flow rate divided by the amount of flow rate. The third parameter we determine is velocity of water flow, which is calculated by using formula 4 times average flow rate divided by the area of spill. By providing the temperature of water, we are able to determine the kinematic viscosity by referring the table 2 given in the lab manual with the aid of interpolation method. After determining the velocity, internal diameter, and viscosity, we can proceed to calculate the Reynolds number. And since all the value of Reynolds number we calculated are more than 4,000, we can say that all the water flow are turbulent flow. The equivalent roughness for different material pipes is provided in the table 1. We also take the table from the textbook as an extra reference. Lastly, the relative roughness is found by dividing the equivalent roughness with the internal diameter of the pipe. So, the parameters determined are summarized in the table shown above. After finding these parameters, we proceed to determine the friction factor from Moody chart by using the value of Reynolds number and relative roughness. Among these 3 pipe materials, PVC can be said as the special one since its roughness is 0, so we determine the value of friction factor by referring the smooth line in the chart. Besides, friction factors also be determined by using Blasius, Colebrook, and Moody formula. All the results are calculated by using specific calculator and recorded in the table below for comparison. From the result, the coefficient of factors obtained from Moody chart for every pipe except the galvanized steel pipe are almost the same with the results calculated by Blasius and Colebrook formula, but it is much more different with the Moody formula. The huge difference between the values of Moody chart and Moody formula, mainly because the accuracy of the Moody formula is about plus minus 5% for smooth pipes and plus minus 10% for rough pipe. Next, for the galvanized pipe, The values obtained from the Blasius formula have large difference as compared to the Moody chart and Colbert formula because it is the simplest and shortest equation which only involves the Reynolds number. Hence, we can say that when the Reynolds number is smaller, the friction factor obtained by using this formula will become larger. Besides, the Blasius formula is not suitable for the rough pipe because the equation does not involve the equivalent roughness of the pipe. Therefore, the friction factor for galvanized steel pipe obtained by this equation is less accurate as it is rough pipe with 0.15 mm roughness. However, it is suitable for smooth pipe such as copper pipe and PVC pipe, which have low equivalent roughness. Furthermore, the coefficient of friction obtained from the Colebrook formula and Moody chart are slightly different since both involve same parameters such as Reynolds numbers, equivalent roughness of each pipe material, and the inner diameter of the pipe. Hence, they are much more suitable for both rough and smooth pipe. As a result, the friction factor of galvanized steel pipe is accurate by using these methods. In short, both Colebrook formula and Moody chart are accurate because they involve the properties of pipes and water flow in the calculation. However, Colebrook formula is not practicable since it involves interaction method which will making the process of the calculation become difficult and slower. So, the Moody chart is the most common method as it applies the Colebrook formula to compute the coefficient or factor of the different materials pipe. Besides, it also summarizes the data in the graph form which will easier the calculation.
Hi, I'm Li Wei-An, and now I'll explain about the discussion 2. According to the calculation, compared with the other types of pipe, the major head loss of the copper pipe is the highest. The second largest head loss is PVC pipe of 20 mm diameter, followed by galvanized steel pipe and PVC pipe of 60 mm diameter, and lastly the PVC pipe of 32 mm diameter. The copper pipe ranks as the highest major head loss because of its highest velocity of water and relatively low pipe frictional coefficient. The factors that affect the pipe ranking or the major head loss of the pipe are internal diameter of pipe, velocity of fluid, frictional factor, and lastly the length of the pipe. Based on the equation above, the larger the internal diameter or the lower the velocity of flowing medium, the lower the major head loss. This means that the major head loss is inversely proportional to the internal diameter but proportional to the velocity of the fluid. Then, since the length of the pipe is set as a constant throughout this experiment, so there is no effect on the major head loss. However, this is also one of the factors that will affect the pipe ranking selection. The longer the pipe length, the higher the major head loss. Another point I want to emphasize is the coefficient of pipe friction increase, major head loss will increase as well. For the turbulent pipe flow, the pipe friction coefficient depends on the equivalent pipe roughness and Reynolds number. It can be seen clearly that increasing the surface roughness of the pipe will improve the friction coefficient of the pipe. From the Moody chart, the coefficient of pipe friction is highly dependent on the flow regime. For discussion 3, when conducting the experiment, to avoid the errors and to improve the existing results, recommendations are listed accordingly. First, the parallax error that is due to the incorrect position of ice caused the inaccurate result obtained from the experiment. To avoid this problem, the eyes of the observer should be in perpendicular to all the measurement scale of the rotameter, manometer, and thermometer. The wrong displacement of eyes may be due to the reason of the observer's height, because it will magnify any parallax error caused by his line of sight being at an angle with respect to the marking. To improve the results, repeat the experiment for a few times and take the average reading, since the average reading will be more closer to the actual reading. Secondly, the presence of air bubbles in the pipe or in the tube may influence the data from the experiment. Air bubbles in the flowing medium often affects the performance of the working system. When the reading of meniscus in the manometer tube, the presence of air bubbles will also affect the slightly changes in the water level. To avoid this, at the beginning of the experiment, ventilation valve was opened for a while to release all the bubbles inside. We need to ensure there is enough time to completely eliminate air bubbles from the tube to maintain its quality. Lastly, the personal errors may be due to the carelessness and poor technique of the experimenter. This is also include the errors in calculating, since this experiment consists of many formulas and calculations to obtain the final answer for further discussion. To ensure the accuracy of the result, the experimenter must carefully record and read the data and carefully check.
Explaining about the conclusion part. In conclusion, this experiment was conducted successfully in finding the friction factors divided by resistance coefficients, even though the data collected are various from the theoretical equation. They have subtle variance and parallel from this experiment. The importance of coefficient factor we gain on using the Moody's map, Glassius, Colebrook and Moody's formula. All of these equations, the Colebrook equation is the most precise since it can be used to determine the both smooth and rough pipe. Unlike the Blassius equation, for the smooth pipe it is more suitable to calculate. The larger the interior diameter or the lower the velocity of flowing medium, the lower the major heat loss, and the longer the pipe length, the higher the major heat loss. Last but not least, the coefficient of pipe friction increases, the major heat loss increases. To sum up, the difference between experimental data and theoretical equation are mainly due to experimental error. Thank you.